This video concerns section 2.1, which is primarily about the tangent line problem. This is our real first calculus topic that we're going to work on, and that is to discover the slope of a tangent line. Tangent lines are tough because you're only given one point and asked to find a slope. The formula for slope really requires 2 points to do rise over run between 2 points. And if you do rise over run on 1 point, you use the same point for both points. The rise is 0 and the run is 0, and the slope is 0 over 0. Yet again, this indeterminate form that we keep seeing, which is undefined quantity. So we're going to start off by looking at the tangent line problem. And this problem was discussed as far back as the 1600s. People were trying to find a reliable solution to this problem, and that is to take a curve and perfectly balance one line right here that touches the curve in that one spot in such a way that it's a perfect balance. It touches that curve, and there's an equal amount of space here and here. In fact, if you zoom in on the curve closely, right at that particular location, what you discover is the closer you zoom in, the more the slope of the curve seems to match the slope of this tangent line. Right here, locally, this curve has a shape or a slope that's a match to the tangent line, but only at that location. So we'll zoom back out here so you can see the big picture. So in many ways, the tangent line has a slope, like every other line, and the tangent line's slope is considered to be a measurement of the curve's slope, but locally, because the slope keeps changing on this curve. As we look at it, it's changing all along here. So the question becomes, how do we discover the slope of a line when we're only given 1 point? So we'll put that as the tangent line up here. And this is C. And naturally, if you look across here, this would be the f of C. C is the point of interest in the x direction, and then we calculate the f of C to get our y value. Well, since we can't really do that, we can't really calculate the slope of a tangent line given 1 point like that with the mathematics that we have, let's rely instead on our ability to get the slope given 2 points. And we'll use the curve to get those 2 points. So I'm going to put another function down here. Let's refer to that as, again, f of x, another function. Here's where I'd really like a slope, which would be at x equals c. And I'll draw the tangent line down there so you can see what we're trying to do again is line this up so that the slope of the line basically matches the slope of the curve right there at that one spot. There we go. So that looks pretty good. We'll call that the tangent line. Now the tangent line again is unfortunately pretty elusive because you're only given 1 point. So what we're going to do is fall back on our ability to get the slope of a line given 2 points. So we'll use the curve because the curve can provide us with the y value very readily. So let's see, how far away are we going to go? Well, let's go delta x away. So delta x means a change in x, and this therefore would be the new x location, c plus delta x. Again, we can move over here. We can line this up with the y-axis. This would be the f of c, and think about what this might be up here. If that's your x value, then this must be the f of c plus delta x. So let's go ahead and draw that secant line. Just like any other line that you would draw on a Cartesian plane, you connect the dots. Let's do that from here to here. Got it. So we can calculate the slope of the secant line, and I'd like to do that right now. So let's do msec. The slope of the secant line is known to be a rise over run on 2 points. That would be the difference of the y values divided by the difference of the x values. And let's write down what we have here. The difference of the y values. Well, here's the top y value. And here's the bottom y value. Here's the larger x value. Here's the smaller x value. Notice that the c's cancel down there. So the slope of the secant line can be written as f of c plus delta x minus the f of c all over delta x. So we do have a formula that represents the slope of a secant line, and we're able to compute the slope of a secant line given a specific function and given a specific c value and a delta x value. We should be able to compute the slope of a secant line. Now, it's not the secant slope that I'm so interested in. I'm more interested in this tangent slope here. So the thought process here is, if you look at the slope of the secant line, it's really not a match to the slope of this tangent line. So the thought process would be, let's make delta x smaller. Let's make it this small here. So I've shortened up delta x, and now delta x is a little smaller. Let's go ahead and draw and see what kind of secant line we would get out of that. Connect the dots. 2 points determine a line. This line's a little better. As we discussed in the preview of calculus, what's happening is as you make delta x smaller and smaller, in fact, make delta x approach 0, the slope of the secant line will just keep approaching the slope of the tangent line. See it leaning over. It's actually kind of leaning down, and if we get a little closer, it'll lean down even more. So I think that really gives us an indication as to what the formula for the slope of the tangent line is. Well, before we do that, you might suspect this, that the slope of the tangent line would be a match to the slope of the secant line when delta x equals 0. That would be a good idea. If you think about it, because as delta x gets smaller and smaller, this line leans over and gets closer and closer to the tangent slope. Let's try this. So is it true? So let's put delta x equals 0 in. Delta x equals 0, and there it is again that we keep seeing this. It's the indeterminate form. So frustrating because the tangent slope is currently claiming that it's undefined, while your eye can see clearly that it does possess a slope right here. I see that slope right there, but it will not reveal it to me. So we have a process that allows this to happen without actually reaching delta x equaling 0, and that's a limit process. So let's use a limit to sort of nudge delta x along to 0, and let's do that on the formula for secant slope. Therefore, the tangent slope should be the limit as delta x is nudged along to 0 on the f of c plus delta x minus the f of c all over delta x. There we go. So what's going to happen here is the limit is going to reveal that hidden value that sort of blinks out right when you need an answer. We're getting indeterminate form undefined. It works everywhere else. So when delta x is not 0, we're getting answers, and we're watching the slope decrease, decrease, and the slope is trending towards a particular value. It just doesn't happen to work where you want it to work, which is delta x equals 0. So what works great to reveal trends in y values, even if the function doesn't work there, which is what's happening here, limits are perfect for that. So the first thing I'd like to do is I'd like to try this formula on a line. Let's make up a line here. -1, -2, -3. And let's do rise over run of, let's run over 1 unit and rise by 2 units. Let's get our ruler out, and this will be my function. Now, what's the equation of such a line? Y equals mx plus b. Well, b is -3. M is run over 1 and rise by 2. Rise over run is 2 over 1. So I guess my function is y equals 2x minus 3, and I know the slope of my line is 2. All right, so I have a question for you. What is the slope of the tangent line right here at, let's say, I'm trying to figure out where we are here. How about at x equals 2? That would be right here. First of all, 2 times 2, 4 minus 3 is 1. So the coordinate of this point is 2, 1. And let's draw a tangent line. Well, it seems like a pretty silly idea. How do you get a tangent line that balances up perfectly? Well, the tangent line just is the line itself. So if you pull this down, the slope of the tangent line is really the slope of the original line. It's 2. So I did this because I really want to know the answer up front, and I want to make sure this formula behaves even on a simple function like a line. So let's try this formula to find the slope of that tangent line. The slope of the tangent line is a limit process. Delta x approaching 0 on the f of, now c is c equals 2. That's the point of interest. So that's going to be c plus delta x minus the f of c all over delta x. And that indeed is how to find the slope of a tangent line of any curve, but it'll work great for this line. One thing I do not want you to do at this moment, if you set delta x equals 0 right now, you got trouble, because it'll say f of 2 minus f of 2 is 0 over 0, and that's just not going to work. So what I recommend is actually run your function. F of x is y equals 2x minus 3. So let me write what f of x is here. F of x is 2 inputs minus 3. So let's run the function. This is the limit as delta x approaches 0. Okay, can we run this function? The new input is 2 plus delta x. Wherever you see an x, from now on you put 2 plus delta x. So it's 2 times input. 2 plus delta x, and it says minus 3 minus, and now f of 2. Well, put your 2 in. That's 4 minus 3 all over delta x. Now, it seems ridiculous. It seems like a lot of work to get our answer, but I got to make sure this formula works on the most simplest of functions, which is a line. We should get 2. Distributive law right here, we get 2 times 2 is 4. 2 times delta x is 2 delta x's minus 3 minus 4 minus 3 all over delta x. This is the limit as delta x approaches 0 of, well, 4 minus 3 is 1 minus 1 is 0. The numbers all zero out, and we get this. Here we are again, guys. If you plug delta x in equaling 0 right now, what are you going to get? 0 over 0. That's not helping me. So why do we keep getting 0 over 0? Because deep down inside, there is an offending factor. And here it is. Delta x equals 0. Delta x equals 0. That's where it's coming from. And when you are able to cancel out the offending factor, you should be able to reveal your answer. Now, we're supposed to, by direct substitution, set delta x equals 0. There is no delta x anywhere in here. The number 2 could care less what any variable is. The limit of a constant is just a constant. So I've proven to you that this formula will give us the correct slope of the tangent line, at least to a line. Let's now try a parabola. And let's actually try a section of the parabola that you probably know the answer to. Okay, here's our friendly parabola, f of x equals x squared. I would like my point of interest to be equal to 0, and I would like to know the slope of the tangent line at c equals 0. Well, come on down here, draw yourself a tangent line that's perfectly balanced right there at that point, and I think you can visually see that the slope ought to come out to be 0, and let's make sure that works. So here comes that formula. We're going to use it. It's called the limit method for finding the slope of your tangent line. It's the limit as delta x approaches 0 on the secant slope, which is f of c plus delta x minus f of c all over delta x. Remember, don't set delta x to 0 too suddenly. The limit as delta x approaches 0, okay, you've got to be a good function evaluator. So you come up here and say, well, input goes into my function squares all input, whatever it is. So my function will simply square that input, c plus delta x squared. That's what it does, it squares input. Minus my function squares input. Okay, let's see where we're headed with this. Let's continue our limit process. Let's square that binomial and see where we are at this point. Okay, c squared, one of each, 2c delta x, and even a delta x squared, and then a minus c squared. This is what you're going to find when you use the limit method. Oftentimes, you will quickly see an arithmetic cancellation, meaning a plus or minus. Now also, I'm looking for the offending factor that I can divide out, and I see it. It's delta x again. Now, these are the only two terms left. Delta x is a common factor, so we bring the delta x out front, revealing what's left, which is 2c plus delta x divided by delta x. There's little wonder why we keep getting 0 over 0, because delta x is going to 0, so that would be 0 over 0. This is the offending factor that we divide out. So delta x approaching 0 on 2c plus delta x. Now, I forgot to put c in there because if you remember, c equals 0. But actually, it's not such a bad thing that I forgot to do that because it's going to come in handy in a little bit. So in our particular circumstance, don't forget we were centering up at 0, and also delta x is now being sent to 0. So this limit becomes the limit as delta x approaches 0 of 2 times 0 plus delta x. Okay, now I can send delta x to 0, and the answer is indeed 0. So I got the slope of the tangent line to a parabola right there at the vertex. The slope looked like 0. The math behind it when I used the limit method came out to 0. Now, why was it such a good idea to leave c until the very end? Because this formula here the only delta x in there is this one. So you get, setting that to 0, you get the limit to be just 2c. So what does that imply? That implies the slope of the tangent line at x equals c is 2c. So that means we can return to this curve, and we can do things like this. I can go here to x equals 1, and I can line up a tangent slope right there at x equals 1. Well, that's really c equals 1. But according to the work we did, and we only have to do it once for this curve, the slope of the tangent line should just be 2 times the current c value, which is 1. The slope of that line is 2. And it is positive, and it's a positive slope. It's positive 2. Now let's come back over here, and let's go to, how about we go back here to c equals negative 2. Okay? C equals negative 2, and we line up. We've run out of curve here, so I got a line way up over there. Draw myself a tangent line. And that's a highly negative slope I'm looking at right there. That's a very negative slope. Well, what slope is that? The slope of my tangent line, according to our calculations, is just 2c, which is 2 times negative 2, which is negative 4. So everything seems to be matching what the curve is saying. So that's a great way to do it, and that is you can either put the c in early, or you can leave it alone until the very end. But ultimately, look for that idea of crossing off delta x's, but you need to be able to factor. So there's two things that happen. There's the arithmetic cancellation, plus and minus usually goes away, the stuff on the numerator, and then a delta x usually factors out front. Okay. Continuing along here, I want to look at one more slope of a function here, and I think we can leave it at that, and that will allow us to discuss the derivative next. This is a curve that is an upside-down parabola whose vertex sits right there at -2. It's also a pretty narrow parabola because of the 2 in front of it there. So I have a prediction. My prediction is here at c equals 1, I should get a positive sloped tangent line. That's my prediction. Take a look at that. I'm sorry, it's a negatively sloped tangent line. So the tangent slope at c equals 1, the only thing I really know is that it's negative. It's going down when you read it from left to right. And let's see if it works. So one more example. The slope of the tangent line is a limit process with delta x going to 0 on the secant slope, which is this formula here. Now we can put c in there if you want, c equals 1. So that becomes a limit process as delta x approaches 0 of f of 1 plus delta x minus the f of 1 all over delta x. Continue that limit process, delta x approaching 0. Well, again, you have to be a good function evaluator. Wherever you see x, we replace it with 1 plus delta x. Wherever you see an x, replace it with 1 plus delta x. So instead of minus 2x squared, we get 1 plus delta x squared. And don't forget to continue the function, minus 2. And minus the f of 1, wherever you see an x, place a 1. So this will be minus 2 times a 1 squared minus 2 all over delta x. This is just function evaluation. Just place that into the function for x, place that into the function for x. There's a bit of algebra to do here, so we have to be extra careful. This is 1 plus 2 delta x plus delta x squared. That's right in here when I squared the binomial. Minus 2. And minus, let's just calculate what we got here. Looks to me like minus 4. All over delta x. Now, it may seem like a lot of algebra, but as I promised, there's some arithmetic cancellation that should occur here. Distributive law, you get minus 2. You get minus 4 delta x. You get minus 2 delta x squared. You just have to be patient, and you have to track these things. Double negative is positive. Don't set delta x to 0 too early, right? Because there's some great cancellation that should take place arithmetically. Minus 2 is 4. Minus 4 plus 4 is 0, so that's all gone. And look what we're left with. Minus 4 delta x minus 2 delta x squared all over delta x. So the last step is typically to factor out the common delta x. After all, that is the offending factor, leaving me with minus 4 minus 2 delta x's all over delta x. Why are we getting 0 over 0 every time we compute this without a limit? Because this is 0, this is 0. By canceling out the offending factor, the limit then reveals itself. And the last step, Now, and only now, can you set delta x to 0 and expect to get a result. Minus 4 minus 2 times 0, the slope is minus 4. So that's how you find the slope of a tangent line using this limit method. And what is it? It's the limit of the secant slope as delta x goes to 0. Arithmetic cancellation first. Actually, function substitution. You got to put that stuff into the function, whatever your inputs are. Spell it all out up top, see what you get. There should be some arithmetic cancellation, pluses and minuses. Those will go away. And there should be a delta x that factors out that cancels with the bottom. And then at the end, you set delta x to 0, and out it comes. Before this time, we kept getting frustrated because we kept getting 0 over 0 for these slopes. They're definitely not undefined. They are defined. We can see them. And this is one method of discovering that. So we're going to take and build upon this in the next video and show you how to find a derivative. And the derivative will help us find these slopes a little more readily, I think.